One of the key benefits of microservices architecture is ease of scale. While going through various deployment and scaling models for microservices, I came across a very interesting scaling model called Scale Cube, defined by Martin L. Abbott and Michael T. Fisher. This model explains how infinite scaling can be achieved by implementing a three-dimensional approach. The x-axis scaling consists of running multiple copies of an application behind a load balancer. If there are n copies, then each copy handles 1/nth of the load. This is a simple, commonly used approach to scaling an application. This scaling model is usually applied where the infrastructure or the architecture is monolithic and the application cannot be split into independent deployable modules. Such applications usually share a common database and a cache and become very resource consuming after a certain threshold. Applications designed to scale in this manner become inefficient with increasing development and application complexity. Also, constant upgrades and releases add more complexity to this model. The y-axis scaling splits the application into multiple different services. Each service is responsible for one or more closely related functions. The microservice architecture supports such a scaling model as there are independent, smaller, fine-grained services with each service having its own database. Combining both x and y-axis scaling with microservices architecture can give better scalability where multiple instances of the same microservice can be deployed with a load balancer. The z-axis scaling model is similar to x-axis with the difference that the individual instances process only a subset of data. From an application development point of view, each instance keeps the same set of code, but at the database level, data is partitioned into different shards. One common component of the application is responsible to routing the request to appropriate application instances. This is a common scaling technique applied in multi-tenant applications. Let's assume you are to develop a server-side enterprise application. It must support a variety of different clients, including desktop browsers, mobile browsers, and native mobile applications. The application might also expose an API for third parties to consume. It might also integrate with other applications via either web services or a message broker. The application handles requests, that is, HTTP requests and messages, by executing business logic such as accessing a database, exchanging messages with other systems, and returning an HTML, JSON, or XML response. There are logical components corresponding to different functional areas of the application. Your objective is to choose the best architectural pattern by making a choice between a monolithic application architecture or a microservice application architecture. Let's imagine that you are building an e-commerce application that takes orders from customers, verifies inventory and available credit, and ships the orders. The application consists of several components, including the storefront user interface, which implements the user interface along with some back-end services for checking credit, maintaining inventory, and shipping orders. The application is deployed as a single monolithic application by using a Java web application consisting of a single web application archive file that runs on a web container such as Tomcat. You can run multiple instances of the application behind a load balancer in order to scale and improve availability. This monolithic solution has a number of benefits. It is simple to develop. The goal of the current development tools and integrated development environments is to support the development of monolithic applications. It is also simple to deploy. That is, you simply need to deploy the web application archive file on the appropriate runtime. It is also simple to scale. That is, you can scale the application by running multiple copies of the application behind a load balancer. However, once the application becomes large and the team grows in size, this approach has a number of drawbacks that become increasingly significant. The large monolithic code base makes the application difficult to understand and modify. As a result, development typically slows down. Because there are no hard module boundaries, modularity breaks down over time. Moreover, because it can be difficult to understand how to correctly implement a change, the quality of the code declines over time. The larger the code base, the slower the integrated development environment, and the less productive developers are. The larger the application, the longer it takes to start up. This has a huge impact on developer productivity because of time wasted waiting for the container to start. It also impacts deployment. A large monolithic application could rapidly become an obstacle to continuous deployment. Updating a single component results in redeploying the entire application, interrupting other tasks regardless of whether they are impacted by the change. There is a chance that components that haven't been updated will fail to start correctly. As a result, the risk associated with redeployment increases, which discourages frequent updates. A monolithic architecture can only scale in one dimension. It can scale with an increasing transaction volume by running more copies of the application, but it cannot scale with an increasing data volume. Each copy of the application instance will access all of the data, which makes caching less effective and increases memory consumption and input-output traffic. Also, different application components have different resource requirements. One might be CPU intensive, while another might be memory intensive. With a monolithic architecture, we cannot scale each component independently. A monolithic application is also an obstacle to scaling development. Once the application gets to a certain size, it is important to form engineering teams that focus on specific functional areas. For example, we might want to have a user interface team, an accounting team, and an inventory team. The trouble with a monolithic application is that it prevents the teams from working independently. The teams must always coordinate development and redeployment efforts. Finally, with a monolithic architecture, you are stuck with the technology stack or version chosen at the beginning of application development. It can be difficult to incrementally adopt a new technology. If your application uses a framework that subsequently becomes obsolete, it can be challenging to incrementally migrate the application to a newer and better framework. The microservice architecture is an alternative architecture that seeks to address the limitations of the monolithic architecture. The microservice architecture defines an architecture that structures the application as a set of loosely coupled collaborating services. It corresponds to the y-axis of the scale cube. Each service implements a set of narrowly related functions. For example, an application might consist of services such as the order management service and a customer management service. Services communicate using synchronous protocols such as HTTP, REST, or asynchronous protocols such as Advanced Message Queuing Protocol. Services can be developed and deployed independently of one another. Each service has its own database in order to be decoupled from other services. This solution has a number of benefits. It enables the continuous delivery and deployment of large complex applications. Services are smaller and faster to test. Services can be deployed independently. It enables you to organize the development effort around multiple small teams. Each team owns and is responsible for one or more services. Each team can develop, deploy, and scale their services independently of all the other teams. Each microservice is relatively small. This makes it easier for a developer to understand. The IDE is faster, making developers more productive, and the application starts faster, which speeds up deployment. Microservices also enables improved fault isolation. For example, if there is a memory leak in one service, then only that service will be affected. The other services will continue to handle requests. In comparison, one misbehaving component of a monolithic architecture can bring down the entire system. Microservices eliminates any long-term commitment to a technology stack. When developing a new service, you can pick a new or different technology stack. Similarly, when making major changes to an existing service, you can rewrite it using a new technology stack. This solution has a number of drawbacks. Developers must deal with the additional complexity of creating a distributed system. Developer tools or IDEs are oriented on building monolithic applications and do not provide explicit support for developing distributed applications. Testing is more difficult. Developers must implement the inter-service communication mechanism. Implementing use cases that span multiple services without using distributed transactions is difficult. Implementing use cases that span multiple services requires careful coordination between teams. There is always a learning curve to developing a microservice-focused team and changing the culture of the organization. In production, there is also the operational complexity of deploying and managing a system comprised of many different service types. The microservice architecture replaces a single monolithic application with multiple service instances. If each service runs in its own container or virtual machine, which is usually necessary to isolate the instances, then there is additional runtime overhead. In order to ensure loose coupling, each service has its own database. A service publishes an event when its data changes. Other services consume that event and update their data. There are several ways of reliably updating data and publishing events, including event sourcing and transaction log tailing.